Hello, this is FlippedHarber for Algebra 2. In this video, we'll be going over Section 3.6, Solving Linear Systems in 3 Variables. Our objectives for this lesson are to represent solutions of systems of equations in 3 dimensions graphically. We also want to solve systems of equations in 3 dimensions algebraically. Our topics include linear systems and solutions of linear systems. Our outline for this video will start by solving a system of equations with 3 variables. Then we'll take a look at what solutions of a 3-variable system look like, and then we'll talk about classifying systems of equations. Now, solving a system of equations with 3 variables is going to be a lot like the elimination process that we did with 2 variables. But we're going to start by choosing 2 equations to eliminate 1 variable. So we'll choose a variable that we can eliminate easily with 2 equations. Then we'll use a different combination of equations to eliminate that same variable. So we have to eliminate the same variable twice with 2 different sets of equations. You'll then have 2 equations with just 2 variables. We'll eliminate 1 variable with those 2 equations. Our last process is going to be substituting back in to find the other variables. Now let's take a look at this system of equations that has 3 variables, x, y, and z. So the first thing I want to do is decide, well, what variable do I want to get rid of first twice? And looking at the z's, I can already get rid of one z just using the second and third equations. And then it's not going to be difficult to use the first equation and either the second or third to get rid of the z again. So I'll start by getting rid of the z using the second and third equations. The way I do that is by subtraction. So I take 2x plus 3y plus z equals 1 and subtract negative 3x minus 4y plus z equals 4. What I end up with is 5x plus 7y equals negative 3. So I've eliminated the z once. Now I need to use the top equation, the one I haven't used yet, and one of the equations that I have used to eliminate the same variable again. So in order to get the z's to match up, either equation I use, I'm going to have to double it so that I end up with a 2z. So I'm going to take the first equation and twice the second equation. So you'll notice it's negative x plus y plus 2z equals 7, the top equation, minus 4x plus 6y plus 2z equals 2. That's 2 times the second equation. Again, I subtract to make the z's go away, and I end up with negative 5x minus 5y equals 5. So I've eliminated the same variable twice. Now what I need to do is use these 2 new equations and get rid of one of those 2 variables. Now obviously what I'm going to go after is the 5 because I have a 5x, excuse me, not the 5, the x, because I have a 5x and a negative 5x. So when I add the 2 equations, I get 2y equals 2. Solving for y, I get y equals 1. Now my process is to go back through the equations, substituting in to get the other variables. So the first thing I'm going to do is substitute 1 in for y into 5x plus 7y equals negative 3. Solving that for x, I get x equals negative 2. Now I go all the way back up to one of my original equations and plug in both x and y, and I find out that z equals 2. Now it shouldn't matter which equation I plug into. I should get z equals 2 no matter which of the top equations I use. So I choose the simplest one to solve for. So I get x equals negative 2, y equals 1, and z equals 2. Now what I need to do finally is just write them in an ordered triple. So it's kind of like a point, but there's 3 of them, so it's a 3-dimensional point. Alright, let's try that again with a different set of equations. Now the reason I chose this one is none of my variables actually line up really great to start with. So what I have to do is make a couple of my coefficients match. Looking through, I can make that 4y look like an 8y. all I need to do is double the top equation. So that's what I did first. I took double the top equation, 6x plus 8y plus 4z equals 16. And I'm subtracting the bottom equation because that's going to make the y's go away. So I end up with 2x minus z equals 15. All right, that's great. So I eliminated the y. I need to eliminate the y again. I need to use a different combination of equations. I used the top and bottom equations. Now I need to use that middle equation. So what I'm going to do is triple the top equation and double the middle equation, because that's going to make my y's a 12y and a negative 12y. So I have 9x plus 12y equals 6z equals 24. That's triple the top equation. 10x minus 12y minus 6z equals 52. That's double the second equation. Now, when I add, whoa, something really magical happens. If I had done this first, I would have found x right away. Both my y's and my z's went away when I did this combination. Now, that doesn't mean that that first stuff that I did is really a waste of time, because now that I know x, I can plug x in and get my z right away. So it's not really a waste of time when I do this and one of my variables just falls out, but it does actually make my life a little bit easier. Now I'm just going to substitute in my x and get my z. So substituting 4 in for x, I find out that z equals negative 7. So now I go back to one of my original equations. I plug in 4 for x, I plug in negative 7 for z, and I solve for y. So my y in this case comes from my top equation. Shouldn't matter which equation I use, just choose the one that you think is going to be the easiest to solve for. And I get y equals 2.5. So my x is 4, my z is negative 7, my y is 2.5. I need to put it in ordered triple form, x, y, and then z. So that's my solution for this system of equations with 3 variables. Let's get rid of that. Okay, so let's move on and take a look at what these equations kind of create in 3-dimensional space. Now, 3-dimensional equations create planes. You can think of a plane as a sheet of paper when we draw it out. So we've got 3 equations that create 3 flat sheets of paper. Okay, a blue, a pink, and a green. Now, it's possible for these 3 equations to create 3 pieces of paper that are parallel, like we see here in this first picture. Now, since these planes don't intersect, these equations can never ever equal each other. So that has no solutions. Another example of what could happen is we could have one sheet of paper that cuts through 2 of them, but the blue and the pink are still parallel. Now that means that the 2 equations are consistent with each other, but all 3 equations aren't kind of agreeing on what's going on. In our last example here on the screen, we see the 3 sheets of paper kind of intersecting each other, but again, they're not intersecting at the same point. Okay, the blue and the pink are intersecting at a different area than the pink and the green and the blue. So all 3 of these pictures represent a situation where there are no solutions for our system. It's what we call inconsistent systems. Okay, now, here's what happens when they actually agree. Okay, if our 3 planes intersect just right, there's one point where all 3 planes intersect. Now this is what we've seen in our 2 examples. We got one point that was a solution for the whole system. Now if the 3 planes intersect in a line, as they do on the right, now this is a situation where we have an infinite number of solutions. There's just point after point after point that agrees with all of them. Now you're going to be asked in some of your problems to classify it, whether it's an independent system, whether it's a dependent system, whether it's an inconsistent system. Well, we looked at 2 examples where it was one solution, it's an independent system. We were able to solve for an x value, a y value, and a z value. if they ask you to classify a system, just start going through the process of solving those equations just like we did in the first two, and one of three things is going to happen. Now, we've already seen ones where you just get an answer. If you just go through the whole process, you get an x value, you get a y value, you get a z value. That is a complete system. It's independent, it's consistent, you've got one point that works. Okay, that's not the big deal. But if you're going through this process of elimination and working the equations together to try to solve it, and you end up with a true statement, that is one that says 5 equals 5. That's a true statement. So that means that you had variables go away totally, and you got a number equals a number, and it's right. That system is dependent. It's where the three planes are intersecting at a line. Now, the other thing that can happen, you don't get an x, y, and z value. You don't get all of your variables to go away, and you've got a true statement. The third option is you have a false statement, something like 5 equals 0. That's not true. 5 does not equal 0. When you get to that point, that means that the system is inconsistent. There's no solution. Okay? It might happen right away with your first two equations you work with. It might happen a couple steps in. But if you ever get to a false statement, you stop, you say, whoa, these systems don't work together. There's no solution. Okay, there's really no better way to learn how to do this than to actually do some of it on your own. So it's time to get started on the homework. I'm planning on spending a couple days on this because it is some pretty serious work. So, time to get started. I'll see you in class, and I'll see you online.